Alright, hi guys. Let's have a look at the VCAA 2014 Specialist Maths Exam 2 multiple choice questions. And again, this is not anything official. It's VCAA's intellectual material. It's copyright VCAA intellectual material, and these are just my unofficial solutions. Question 1. The asymptotes of the hyperbola given by that thing there intersect the coordinate axes. Now this is the asymptotes of the hyperbola. Intersect the coordinate axes at. Alright guys, I think this is pretty easy to do without CAS. I wouldn't bother with CAS because the keystroking takes quite a long time, and you can often do a wrong keystroke and then get the wrong answer and all kinds of dramas. So if they're easy to do manually, I do them manually. The asymptotes are found by neglecting the 1. That's right, you neglect this 1 here and you'll get the asymptotes, and then you just solve that as appropriate. So we've got that equation there. Now all we need to do is to set x equal to 0 to work out where the y-intercepts are, and then set y equal to 0 to get where the x-intercepts are, and we're laughing. Okay, so that's the solution for the asymptotes once you solve that equation above. Okay, and then when y is 0, you get x is 3, that is the x-intercept of where the asymptotes hit. That's 3 and 0, and then when x is 0, y works out to be plus or minus 2, which gets you 0 and minus 2 and 0 and plus 2, and that gets you option B for you and me. Yippee! So, but if you really are a CASy person and you want to use the CAS, let's go over the page and we'll show you how you would do that. Well, it's very simple actually. Plug the whole beastly thing in and then just go solve for this thing equals 0 for y, given that x equals 0, that gets you the y-intercepts here. And then you can do a similar little trick on it by just getting a history recall, going down there and changing this bit in here, solving the same thing with the 0 here, not a 1 here, remember, for the asymptotes this is, for x, given that y equals 0, that gets you the x-intercept at x equals 3. And that gets you the answer. Okay? Question 2. We've got an ellipse given by this thing here, has centre, length of horizontal semi-axis and length of vertical semi-axis respectively of. Alright, why don't we just do a little bit of completing the square, and then I think we'll become aware of what's going on. I wouldn't bother with CAS with this, not at all. It's quite simple to do in a few seconds. So I've completed the square on the x bit here, adding 9, subtracting 9. Then I've taken 2 outside the bracket and I've completed the square with the y squared and the 4y terms in here. And then all I've got to do now is get that minus 4 out of that bracket and then go for it, guys. That's yes, that's right. I've taken the minus 4 out, remembering to multiply it by 2. Yes, great. Now, that's looking good. That's okay. I've just got to turn this into y plus 2 all squared. And I think we'll have the answers to all our questions that we need, won't we? So what are we saying? Centre would be 3 and minus 2. And the x semi looks like it's 1 because this thing's divided by 1 squared. And this thing's divided by a half. And then of course that becomes 1 over root 2 all squared. So I'm getting ahead of myself. That's what we get there. So yes, the centre is 3 and minus 2. The x semi is 1, and the y semi-axis is 1 over root 2. And is that somewhere? Oh yes, it's number E. Great, alright. We're sizzling along. Let's do another one now. Question 3. This is actually a very curly little question. In fact, I think it's more of a methods question than a specialist maths question. In fact, I've never seen a question like this on a specialist maths paper. If we had the presence of mind to factorise the numerator and the denominator, we'd get a pretty good handle on what's happening, because you'll notice there's an x minus 3 here and an x minus 3 there. And in fact, that's the key to all this discontinuity mumbo-jumbo here. They talk about asymptotes and points of discontinuity. When I first saw that, I thought, what are they talking about? Well, actually, they're just talking about a hole in the function, a small hole in the function where it's discontinuous at the point where x equals 3. Because this is not defined where x is 3 or x is minus 2, is it? Because that would get you 0 on the denominator, which is verboten, can't have that. So let's cancel out the x minus 3's, and then you can see that the function is actually just x minus 1 over x plus 2, remembering that it's not defined where x is 3, because that disappears out of the picture. So now we can easily turn that into something which we can recognise, which I've just started to do there for you, making the part of the numerator the same as the denominator and then compensating with this term here. That numerator is x minus 1, which is what we've got up here, but I'm doing this little trick, which you should put in your little toolkit of tricks to do when the degree of the numerator and the denominator are the same. This is a really useful trick instead of long dividing. So you get that. Now we know what this thing's doing. It's just simply a rectangular hyperbola, which we're very well used to, with a few little transformations here and there, and a discontinuity when x equals 3. See that? There's a hole in it, guys. There's a hole in it. Alright, now let's just go up here and see what's going on. We've got an asymptote where, wait a minute, discontinuity with x equals 3. They're the two options there. So what's this? Asymptote where x equals minus 2. Looks like that one. D for you and me. Yippee. Now, if you did want to do this with CAS, you could have a go at it the following way, but it's a little bit dodgy because you really wouldn't know how to get this discontinuity thing happening unless you're a bit lucky. I'll show you what I mean. This is with a TI CAS handheld that we use at my school, by the way. You put this in as function f1 of x, right? Then, okay, the CAS handheld is smart enough that if you repeated back to yourself, what is f1 of x, but why would you know to do that is my question. But if you did, you'd just get this. But you'd have to have the presence of mind to realise that the thing is not defined at x equals 3. And this is, here's a prop fraction command here to turn it into the form that we wanted to work out where the rectangular hyperbola is. And the asymptote for it is it's minus 2, and this transformation thing here, it's an upside down one and moved up by 1. But you'd also have to have the presence of mind to put in f1 of 3 and get an undefined to sort of know what was going on. And I don't think you'd actually necessarily realise to do that if you did this thing with CAS. So I wouldn't be doing it with CAS, I'd just do it the old tried and true manual way. But this, at the very least, might teach you a few commands to use with the TI CAS handheld, if that helps you, okay? So therefore, the option was D. The answer was D, wasn't it? Okay, next question. Well, this one's a nice, easy little question. No tricks, no grenades, no nothing. We should all be able to do this question quite easily, guys. So I would do this manually because it's just a piece of cake, this one. You know that whatever's in here has to go between minus 1 and plus 1 inclusive, so then you just solve it for x, just like that. So, adding 1 to both sides, you get 2x goes from 0 to 2 inclusive, and therefore x would go from 0 to 1 inclusive, which is C for you and me, which is very nice, isn't it? That would only take you a few seconds, that one. In fact, you could probably do that one in reading time, which I'd highly recommend, by the way. For CAS confirmation, in case you're a CAS nut, you can do this. You can look through the catalogue on the TI CAS handheld. You can't get this one through the menu. You can go through the catalogue under D, and you can go for domain of this thing here, comma X. And as I say, it's only available from the catalogue, so it's not very convenient. But you will get this here, in case you're having a mental blank on how to do it manually. So the answer is C. Alright? Question 5. Now this one is a very nice little question as well, nice and easy, and actually we can do this manually or with the CAS handheld, TI CAS handheld, and either way is peachy keen, really. Here's the manual way, which I'm used to teaching all my students to do, so let's do it that way. It only takes a few seconds. Z is 2 root 2 cis 3/4 of pi, and therefore, of course, Z squared is just going to be 2 root 2 all squared cis of twice the angle, so 3 pi over 2. So after you just fiddle with this a bit, you'll just get minus 8i, because cis of 3 pi on 2 happens to be, now let's think about that, well, it's just minus I. It's just minus I. So 8 times minus I gets minus 8i, doesn't it? So is that somewhere? Yes, it's option A. Hooray for option A. Now, as I said, if you were a CAS nut, we would do it this way. For CAS confirmation, you would use the exponential, yes, the exponential form of a complex number. Now, guys and gals, I need to explain to you that the TI-CAS handheld device calls polar form what I would refer to as exponential form. And it's in this form here. RE to the I theta is actually very easy to unravel as the same thing as R cis theta, which we understand as polar form. Okay, now if you put that in there as the number, e.g. 2 root 2 e to the I 3/4 of pi, and then you just square it, you'll get your answer very easily. And there it goes. I've got z is set to equal this, right? See that thing there? And then it just spits this out as the answer, which is in Cartesian form. And then you can just square z and you get the answer, minus 8i. Alright? So that's a really nice little trick for you. You can now do polar form in the TI-CAS handheld as this exponential form equivalent. Okay, just remember RE to the I theta is the same as R cis theta. Okay, now that's option A as we were saying. Alright, now question 6. This is just a little playing around with the index laws kind of question, guys, and the CAS is totally unhelpful for this, so you just plug away at it by hand and you'll be pleasantly surprised how easy it is, even though they try to make them look hard. We know that I to the 2n plus 3 is what we have to find out. They've given us I to the n is p, and we know that I squared is minus 1. So you just basically just reframe this in terms of these building blocks. So I to the 2n plus 3 would be I to the 2n times I to the 3, wouldn't it? Because and that would be I to the 2n, of course, is I to the n squared, and we know that I to the n is p, so that's going to be p squared times minus I, won't it? Which of course will be minus ip squared, and that is number D for you and me. Alright, question 7. The sum of the roots of that complex polynomial equals 0, where z is a complex number is. Now they're asking for the sum of the roots, and of course, guys, we know there'll be 3 roots because this is a cubic, and therefore this one, look, this is an absolute dead set CAS question. You just go for the CAS. So there are actually 2 ways that you could do this. The way that I'd be more used to doing would be this way, where you just go for the C solve. That's complex solve, which is in your algebra menu for complex numbers on the TI-CAS handheld. This here I've used X. It doesn't matter if you use X instead of Z, it's all the same. And you get these 3 roots, no problem. So then you've just got to do a history recall on this thing down to there, and then just get rid of some of these words and just put pluses in between them and add them up and you get 5. Alright? So the answer is going to be E. Now the other one that you may not be quite so familiar with is this one. Zeros, C zeros, that's complex zeros, which you access from the same spot, algebra and then complex under the algebra umbrella, and I've put Z's here. Now, what you do here is, you'll notice here the polynomial is here, but there's no equals 0. It's just the polynomial stated then comma Z, and what it does is it gives you the roots, or the zeros, as a list in these curly brackets, alright? Now, what you can then do is you can just go for sum, and then do a history recall on that list, and it'll just add up the list for you, without any messing around. You'll just get the answer 5. So that's a nice little one to have in your tool chest of little tricks for the CAS, alright? And the answer is E. Alright, question 8. I'll finish on this one for this particular video because I don't like to go too far over 15 minutes for all these things, and then I'll do the rest in subsequent videos for you. Question 8. The principal argument of this is, well guys, you could slug away and do this one manually, and there's nothing wrong with doing that. Or you can just go straight for the CAS, and that's an absolute whiz. So that's what I recommend in this case, and I'll show you. You just use the CAS, and then you go for the angle command. Angle. That's down in your complex number menu under number tools, under complex, under the number tools umbrella. So you just put this whole expression in here and just angle of it, and it just spits it out. Look, 11 pi on 12. I mean, is that good or is that good? That's option C. or if you want to do it manually, or if you're not using a TI CAS handheld device, say a Casio or something else, I'll show you the manual way, which I would be showing my students anyway, as follows. For the numerator, we know that we have minus 3 root 2 minus root 6i, so we've got to basically go this way in the negative x direction by 3 root 2, and then down this way in the negative y direction by root 6 units, and therefore the angle in here, this little alpha angle as I've labelled it, is the angle whose tangent is just this distance, root 6, over this horizontal distance here, which is 3 root 2. Don't worry about the minuses for now. So this little angle alpha is the angle whose tangent is root 6 over 3 root 2, which happens to be this angle here, root 3 over 3, which is 1 over root 3, which is pi on 6. Alright, now, having got this little angle alpha, we have to now turn that into the argument, the principal argument of the numerator term here. That's the argument there. And we can see we're travelling in a negative direction from the positive direction of the x-axis, so it's a minus 5 pi on 6 argument for the numerator. Now, similar procedure for the denominator. We'll draw a little diagram to get your bearings right, guys, and we know that we've got positive 2 units in the x and positive 2 units in the y, which gets us an angle of course, it's pi on 4. Therefore, we're set to go now. We know that the argument of the denominator is pi on 4, the argument of the numerator is minus 5 pi on 6, therefore the argument of the numerator over the denominator is the argument of the numerator minus the argument of the denominator, and that's going to be minus 5 pi on 6 subtract pi on 4. Converting them to 12ths, you'll get minus 10 pi on 12 minus 3 pi on 12, which is minus 13 pi on 12, which if you then convert back into principal argument land by adding 2 pi, you will get 11 pi on 12, which is exactly what we got with this little calculator method up here. So the answer is C for you and me. Yippee.